before I actually write down the next result, I repeat the previous picture. So this is our vector space V. Let's say somewhere we have a subspace W, and we just learned that there's some kind of a unique subspace W complement. Such that by definition, every red vector is perpendicular to every green vector. So they are perpendicular, with, where again, what it means perpendicular will depend on your inner product. And every vector in the space V can be decomposed into a vector in W complement and in a vector in W. So that's what we have shown until now. And now the next thing, that is a small result, which our book just has here, so I like to show it to you, is what about if we start with W perpendicular? So what about if you do this W perpendicular, also orthogonal, that's a subspace, so we can make the orthogonal of the orthogonal. And for my picture, it's clear what's happening. If you look at all vectors which are perpendicular to red, we are back to green. No? So from the picture, it very much looks like, oh, for my picture, it has to be back here. No? The only trouble with the picture is we don't really know what our inner products are. And keep in mind, this is just two-dimensional. And we are talking about general spaces. Maybe in 17 dimensions, things get different than in 15 or something like this. It turns out, again, the general assumption in linear algebra is if you see something good in 2 dimensions, very often it's good in every dimension. And so it turns out this is actually true. And that is in your book, Theorem 6.25. If you have V, an inner product space, again, that means it's a vector space with an inner product. W in V, a subspace. Then nicely, W complement, the complement is back to W. So this is what is always true. So let's try to show this. So the first thing is, we go back to the definition. What does it actually mean if a vector is in U in W complement? That means if you take U and you multiply it with any W in large W, it's always 0. No? This is your space, the big one. And now this means for all W, that means what about if I take W in W? If I take now any U in W complement, for all U in W complement, no? Because that's the only way how an element can get into W complement, it has to be 0. And now we think, what does this actually mean? It means every W in W is orthogonal to every element in W complement. So that means W is in W complement complement. But this is now true for every small W. So therefore we have shown, okay, I make it like this so you see that the set is actually a subset of W complement complement. So this is okay. We like to show they are equal, no? So we like to show they are equal. Now we have shown this is part of this. If we now also show that this is part of this, we are done. Because then A is part of B, B is part of A, so both of them have to be the same. Okay, so how do we do this? And this is actually now where our result which we proved before the break comes in handy. So let's take an arbitrary element here. So let's take, how did I call it? U. So let's take an arbitrary element in complement. Then we know we have this decomposition of our vector space. Therefore, we know U is equal to U1 plus U2, where U1 is an element of W, and U2 is an element of W complement. And also because it's an element in W complement, we also know that if you multiply U by any element in W complement, so how do I call these guys now? V is equal to 0 for all V in W complement. That is just the property what this complement means. It means you have to be perpendicular to every vector here. But now we see, oh, so U can be written like this, and it's 0, the inner product, for every element in W complement. So for sure, I can also multiply by U2. So that means 0 is equal to U. And now I can put any element in W complement, so I can especially take U2. Okay, but now U is U1 plus U2. That's how we got U1 and U2. Now we learned that we can actually distribute for inner products. Now U1 is in W, U2 is in W complement here. So this here is 0, no? So we have U2, U2, which is the norm of U2 squared. So now we know 0 is equal to the norm of U2 squared. That means U2 is equal to the 0 vector. And that means U equal to U1 plus 0, it's equal to U1, is an element in W. So now what did we show? Every element in W complement is an element of W. So that implies W complement is an element, is a subset of W. So now we have W as part of W complement. Very, very smartly written for me here. Okay. Sorry. And then we have W complement is part of W. So this is part of this is part of this. So the two sets are the same. Therefore, W is equal to W complement. Okay, so in your picture, you go from subspace to the complement. If you do another complement, you come back to where you started. That is what this says. So the complement of the complement is your original subspace. Okay, so again, that's a nice property to have. Funnily, certain things like this here, they actually break if you have infinite dimensional spaces. Then you have to be a little bit more careful, but okay, that is not part of our class. Okay, so twice the complement brings you back to where you started. And as I promised, we end the class with Gauss algorithm.